Hello, welcome back to lecture 10 of this course on tectonics and geodynamics. So, lecture 10 will now be dealing with triple junctions on a flat earth, something that we started off in the last class and I'll just continue with here. So, what we were discussing, if you remember, was with respect to the stability of what we call triple junctions. So, we'll continue with looking at the stability of triple junctions and wondering exactly how a triple junction stability can be evaluated, right, from knowledge of what we have. So let's just first of all look at the type of triple junction we were discussing. And if you remember, the type of triple junction we started off with was with a very specific configuration, right, of three types of boundaries, in which we had a plate A, a plate B, right, and a plate C, in which plate A, sorry about that, yes, here, and you had a plate A, a plate B, and a plate C. Now, if you remember, plate A was overriding both plate C as well as plate A, right? So it means the apices of these triangles are actually pointing towards plate A, which means plate A is the overriding plate. And then you have plate B and plate C, in which case also, right, we have plate C overriding plate B. So we have two systems here. Now, if you remember, the type of velocities we had were roughly, we did not give you any exact values, but it was a sort of value which was like this. So in which the velocity of C with respect to A was such that it was almost orthogonal, right? The velocity vector was almost orthogonal to the orientation of the boundary, whereas the relative velocities between plates B and C were not exactly orthogonal. They had a component of strike parallel movement as well, but it was largely convergent. So that is why these are effectively trenches. So this is what we call a TTT boundary. Now, the question that we started off with is actually looking at the nature of this triple junction. So this was the triple junction we were worrying about. So the question we wanted to answer is whether this triple junction is stable or unstable. So those are the catchwords, right? Is it stable or unstable? Now, the way we looked at it, right, if you remember, was thinking of all of these plates being made of glass, and we were looking at it from above. So what we were thinking is plate A is overriding plate B. So if we consider plate A to be completely static, so we consider plate A to be the static plate. So plate A is the static plate and it's overriding plate B. So if this boundary, these two boundaries remain exactly where they are, so the position of the trench is attached to the overriding plate. So therefore, if I fix the position of plate A, that means this margin is effectively considered fixed with respect to the other two. So let plate B and plates B and C, let them move with respect to plate A. In this case, then we saw that, I mean, if plate B had to move forward, then plate B would have moved to somewhere along here, right? Similarly, right, if plate C had been allowed to move forward, right, with respect to plate B, so it would have been somewhere here. So what we would have seen, right, is if plate A was completely made of glass, then the frontal edge of plate C would have been at this position, this particular position with time, and this particular position here. The frontal edge of plate B would have been in this position. So we would have seen all of these below plate A. Now we would have seen this below plate A, but what about this margin? This margin here is below plate C. I mean, this, because plate C is overriding plate B. So effectively, because we will not be actually able to see through plates, it means that this segment of the boundary and this segment would not be visible to us. These two have been fixed by us because that is how we are looking at the problem. So effectively what would happen is that the boundary between B and C would move from this position northwards to this position. So to an observer on plate A, right, so if a person was situated somewhere around here, let's say here, initially that person would have been looking at the boundary between plates A and B. Now would have been at the boundary between plates A and B. Now, as this boundary actually moves northwards, right, then the position of this particular boundary changes, and after some time, this person would have been looking at the boundary between plates A and C now, instead of plates A and B. Now, what this means is we work this out in a sort of roundabout fashion. So the configuration we would get, right, ultimately would actually be something of this sort. So this is what would result. So the boundaries would be, this would be a subduction zone, this would remain a subduction zone, and this would remain a subduction zone, except the triple junction has moved from this point here, right, upwards to this particular point. Now, this movement of the triple junction up means that the configuration here, so initially, if you consider the disposition of the triple junction, this is what the geometry of the three boundaries was around this triple junction. Now you can see that the boundary around the triple junction is this configuration. So it has changed from this geometry, it has actually changed to this kind of geometry. So in other words, this configuration was obviously not stable. On the other hand, if we look at this particular configuration here, right, if we look at this particular configuration here, it's actually moving northwards with time. So with the next increment of movement, the position of this boundary would actually move a little bit further northwards. So if it moves further northwards, right, then effectively the disposition would remain the same. The geometry of the plate boundaries around this particular triple junction would remain exactly the same. So effectively this geometry is stable. Now, as I said, right, what we've done so far was looking at it in quite a complicated manner. Is there a simpler way to actually evaluate this, right? Can we actually look at a TTT junction and try to look at it in a simpler way? And indeed, we can then use the relative velocity triangle system that we were using all the time through. So we look at it using the concept of relative velocities, and we exactly use the same thing. So once again, we write out a favorite formula here. So the relative velocity of C with respect to E would be the relative velocity of B with respect to A plus the relative velocity of C with respect to B, right? So now if I plot the relative velocity of B with respect to A, now B with respect to A, if you remember, so this is B with respect to A. So if I now, let's use the black pointer for the relative velocity triangle. So if this is my point A, now B, to an observer on plate A, B is moving this way with time, right? So this would be the position of plate B, right? I'm taking it directly from here and using it here. So B with respect to A, and then you have C with respect to B. Now this boundary here is B with respect to C. So C with respect to B is exactly the opposite of this. So it would be in this particular direction. So this would be the relative velocity of C with respect to B, which means the relative velocity of C with respect to A would be something like this, which is exactly, you can see, around here. So it's supposed to be parallel to this. So any deficiencies, it not being actually parallel, is simply because I've not drawn it perfectly, but I think you can just correlate the two and understand what I'm saying. So this is my relative velocity triangle. Now, sorry. How do we now begin to look at the stability of this particular triple junction? Can we look at it in a simpler way? Well, one of the things that we can do is we can use on this relative velocity triangle, we can actually now try to plot in positions along which, right, where the orientations of the boundary be. What configuration would the triple junction have? Now, one of the fundamental things that we can start off with is thinking that a triple junction, right, simultaneously must have the velocities of all three plates. So this is something that a triple junction, that is characteristic of a triple junction. So if it has the velocities of all three plates together, then when a triple junction is actually moving, so if the triple junction, right, say with respect to plate A, because the trench, let's say the boundary between plates A and B, the boundary between plates A and B is actually attached to plate A. So therefore, the position of the trench does not change with respect to the position of plate A. However, for a person on plate B, right, the trench is actually moving in this particular direction with time. It's moving in this direction with time. It's moving to roughly towards east, northeast. Now, however, is there any other way that the boundary itself, if we just imagine that the boundary between plates A and B can move independently of the two plates, just imagine for a moment, is there any way we can think of the boundary being able to move such that to an observer on A and B, its position does not appear to change with time? So one of the only ways in which the boundary can do that is that if the boundary, because our assumption is that every point along this boundary, so whether it's you're looking here, 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 any point along these boundaries, all of these points actually look the same to an observer. So an observer will not be able to discriminate between a point here and a point here and a point here. So effectively all points in the boundary we assume look the same. So therefore, if this boundary were able to move parallel to its own trend, so this is now oriented north-south. So if the boundary actually moved north-south, right, exactly parallel to itself, then to an observer on A and B, even though the points along the boundary that he or she are facing may change with time, the person would not be able to make out the difference, because to us, for all practical purposes, all points on this boundary are identical. Therefore now, if we assume that the boundary can move parallel to itself, then in that case, movement of the plate boundary parallel to its own trend would not effectively change the position of the boundary with respect to an observer on either plate. So what we do now is we now think of all possible velocities. What kind of trend can the boundary have so that its position does not change? We know that the boundary is attached to plate A. What we do is we draw a dashed line passing through plate A, because we know that the trench itself is attached to plate A. So if the trench between plates A and B moved north and south, right, it moved in this direction or in this direction with respect to plate A, then effectively to any observer either on plate A or on plates B and C, the position of this plate would not appear to move. Now, therefore, this is the way in which a plate boundary can actually move in such a way that its position does not change to observers on any of the plates. Now, let's just get back to the next orientation. Let's say the boundary between plates A and C, this boundary. Now, the boundary between plates A and C, right, is there any way that this plate boundary can move, right, such that to observers on plates A and C, its position does not change? Once again, it's the same thing. If the trench can move parallel to itself, then effectively to observers on either plate, right, there would appear to be no change in the position of the plate boundary. So then what we can do is draw another dashed line. Once again, this plate boundary between plates A and C, because A is the overriding plate, the trench is attached to, attached to plate A, and therefore what we can do is draw a line parallel to the boundary between plates A and C through point A of the relative velocity triangle. So now this, we can actually call this boundary AB. Let's call this boundary AC. So this is the boundary between, this is the way in which the plate boundary between plates A and C can move in such a way that the position of this plate boundary apparently to an observer does not appear to be changing with time. Now let's get to the boundary between plates B and C. Now the boundary between plates B and C is this one. This is the original position of the boundary between plates B and C. Now if I have to think of this boundary, this is obviously attached to plate C. So the position of this boundary on the relative velocity triangle would be at the point which is represented by plate C. Now on top of that, now if this boundary moved parallel to itself, so this boundary, as you can see, is oriented east-west. So if it moved east-west parallel to itself, then to an observer on plates B and C, its position would not appear to change. So therefore, the only way the boundary between plates B and C can move such that its position does not appear to change to observers on B and C is by moving parallel to itself. And in that case, what we need to do is to draw a dashed line representing all possible velocities of the boundary between plates B and C such that its position does not change to an observer on either of the two plates involved. So now, as you can see, we have three intersections. This point here at point A is the intersection between the AC and the AB boundary, and this one here, let's call it the BC boundary. So this dashed line here, the one which is east-west, is represented by the east-west line, right, that represents the velocities, all possible velocities of the boundary between plates B and C. Now, as you can see, the intersections we have, this point here represents the intersection of plates, the boundary between plates B and C with boundary between plates A and B. This point here is the boundary between plates B and C, and this point here, boundary between plates B and C, and the boundary between plates A and C. All three of them, right, the triple junction by definition has to simultaneously have the velocity of all three plate boundaries together. As you can see, there is no unique point, right, which can represent the position of these three boundaries. That is how we can tell that a particular plate boundary position is unstable. So because all three of these boundaries do not meet at a point in the relative velocity triangle, therefore this particular boundary, this particular configuration, that is this configuration, is unstable. Now, what of the new position? So the new position is here. So this is the new position, the new configuration. In this case, what would happen? The boundary between plates A and B, right, would remain the same. It's still oriented north-south. The boundary between plates B and C, the boundary between plates B and C, right, this is the boundary now. This is the new position of the boundary. The boundary between plates B and C is still east-west, and it's still, C is still the overriding plate, so it would still pass through here. So let's actually give it a different color so you can follow. So now for the next one, so suppose this is for the new position here, so C passes through here. Now let's take the boundary between plates A and C. Previously the boundary between plates A and C was this one, but now the new boundary between plates A and C has a north-south configuration. So this is plate A, this is plate C. So the boundary now is north-south and it's collinear, right, with the boundary between plates A and B. So therefore now here the boundary between plates A and C would actually pass through plate A, but it would also be oriented north-south. It would be coincident, right? It would be coincident with the AB boundary. Now, as you can see, the AB and AC boundary are coincident and the BC boundary is here. The two lines will obviously meet in a point. So this then means that all three of these lines are now meeting at a point. Therefore, this particular configuration we have is a stable triple junction. This is a stable triple junction because they are all meeting at a point. Not just that, oops, I keep on rushing. It means that if I'm here, that means the position of the triple junction, this point can be taken to represent the relative velocity of the triple junction with respect to plates A, B and C. So to a person on plate A, the triple junction appears to move northwards, which is exactly what you see. To a person on plate B, the triple junction would actually move towards the northeast with this kind of velocity. To a person on plate C, the triple junction will continue to move eastwards, right? Eastwards, and the velocity will be equal to the magnitude of the velocity here. So this way, we have a much more direct way of evaluating, right, whether a particular type of triple junction is stable or unstable. Now, what does this mean? If we go to the next one, it means that you can consider a triple junction to be stable when the lines that represent the orientations of the plate boundaries on the relative velocity triangle, they all meet at one single point. So this is actually the essence of it. The stability of a triple junction, first of all, what we do is to draw the relative velocity triangle. Once you draw the relative velocity triangle, there on that triangle, you actually mark in lines attached to the particular position of the boundary, right, on the appropriate position of the plate boundary on the relative velocity triangle, and draw a line which is parallel to the orient trend of the plate boundary itself, the strike of the plate boundary. If all three of these lines, they meet at one single point, then the boundary is considered to be stable. If it doesn't, it's unstable, and an unstable triple junction will be expected to evolve into a stable geometry with time. So this is effectively the way we actually look at this. Now, let's just look at a different type of triple junction. Let's take a triple junction which is an FFR triple junction. Once again, let's use the black color, right, to actually draw in the line. So an FFR means you have two transform faults and a ridge. So let's consider now a ridge which is oriented north-south, right? So let us say this is plate A and this is plate B. and let's say that we have a plate C here, and the boundaries between plates B and C. So let us say that the spreading is orthogonal, right? So it is orthogonal this way. The boundary between plates B and C, let it be a dextral transform fault, and the boundary between plates A and C, let it be a sinistral transform fault. Okay, so we have a combination here. So this is an FFR triple junction, right? It's a fault, fault, ridge triple junction. Okay, now this kind of junction, is it stable or is it not stable? We've looked at trenches, right? In this case, now how do we begin to look at the positions of these? Now the first thing to do once again is to draw the relative velocity triangle, right? Now I've not given you exact values, but let's draw it the way we do. So once again, we'll do it assuming that the relative velocity of C with respect to A is equal to the relative velocity of B with respect to A plus the relative velocity of C with respect to B. So let's just follow the same strategy we've been following. So if this is, okay, let's do it here. So we have point A here. Let's say this is point A. Now to an observer on point A, plate B appears to move this way with time. So this position here represents the position of plate B to an observer on plate A. Now to this we have to see how plate C is moving to an observer on plate B, right? So plate C, how is it moving with respect to an observer on plate B? So now with respect to an observer on plate B, right, we know that it is actually moving this way with time, with northeastwards with time. So C with respect to B would be parallel to this. So we can now draw it this way. So this position would be the relative velocity of C with respect to B. And as expected, when I join A and C, you can see that this boundary, right, with this arrow is exactly parallel to this arrow. So which proves that this also is a boundary, right, that is showing a strike slip configuration. Now I've drawn it particularly badly, so let's just shift it to here and make it a little more central, right? So it's like this. So this is point B, this is A, and this is C. So I have my arrows here, I have an arrow here, right? So let's just take it this way, and this is the other arrow. So the arrow positions are not all that important. Now let's also, just to prevent confusion, let me just wipe out this part here. So let's get rid of that and get back to the pen. And now what I'll do is use the red one. Now using this particular strategy, how do we now begin to look at the relative velocity between, how do we plot in the positions of the boundaries, right, on this triangle? So we'll use the same principle. On the relative velocity triangle, we have to draw in lines which are parallel to the orientations of the boundaries. So let's take the boundary between plates A and C. So this is the orientation of the boundary between plates A and C. Now in the case of the trench, the boundary was supposed to be attached to plate A. What would happen in the case of a transform fault, in the case of a transform boundary, right? So what do we do? In this case, what we do is we assume that the boundary is actually parallel to the AC side of the triangle, and that has to be, because the orientation of the boundary, by definition, a transform fault, the velocity vectors are parallel to the trend of the boundary. So here now, if I draw in the AC boundary, right, so this would be the AC boundary, and it would pass along the side AC of the triangle. Similarly, if I look at the transform boundary between plates B and C, here too, the orientation of the boundary would be parallel to the BC side of this triangle, because the relative velocities and the orientation of the sides of the triangle for this kind of case are parallel, right? So this is the BC boundary. Now, what do we do about the boundary between plates A and B, which is a ridge? So in this case, when the boundary between plates A and B is a ridge, what would be the relative velocity of a ridge, of a point on the ridge with respect to either of the plates? Now here there is a slight difference to what we did with respect to the trenches or with the transform faults. Now a person who is on the ridge, precisely on the ridge, and a person here. So to an observer, let's say on plate A, a person will observe plate B to be moving with the velocity equal to velocity of B with respect to A, that is this one. How about the ridge itself? How does the ridge move with respect to an observer on plate A? Now the ridge itself is located exactly at the middle point and is actually just the only velocity that an observer in plate A will be seeing is that the ridge position is fixed, but the observer himself is moving westwards. So therefore, to a person who is on the ridge, to an observer is on plate A, the ridge will appear to move eastwards with the half spreading rate, not with the spreading rate, but with the half spreading rate. So therefore, it would be exactly half the relative velocity of that between B and A. So in other words, the velocity of the ridge would be represented by a point which is the midpoint of the side of the relative velocity triangle represented by AB. Now, how must this boundary move so that its position does not appear to change with time? As I said before, it has to be parallel to the orientation of the ridge. So this is the orientation of the ridge. So what we need to do is to draw a line, right, which is this way. So this represents the boundary between A and B, all possible velocities of the boundary between A and B, in order to see that the position to an observers on plates A and B, the position of the boundary does not change, right? That is the idea. However, now you see now that whether or not these meet at a point, it really depends on the magnitudes of the velocities of the AC velocity vector and the BC velocity vector. If the AC velocity vector, that is this side and this side of the triangle, are exactly equal, that is, if the triangle turns out to be an isosceles triangle, in that case, the perpendicular bisector of the line between A and B, because it's orthogonal spreading, the perpendicular bisector of the lines between A and B would pass exactly through point C. In that case then, as you can see, all three dashed lines, AB, BC and AC, are meeting at a point on plate C, and the triple junction then would be exactly stable. The triple junction then would be exactly stable. However, if we have a situation where this is a sort of scalene triangle and not isosceles, then obviously the perpendicular bisector will not pass to point C, and in that case, right, you will not get a common point of intersection. So therefore, the nature of this junction, that is the FFR junction, it may be either stable or unstable depending upon the configuration, the actual magnitudes of the relative velocities. So there are conditions under which it will be stable, there are conditions under which it will not be stable. So an FFR junction, as you can see, right, it has these conditions here. Now, what does this imply for FFF junctions, that is tree transform faults? So just imagine that if you had junctions which were like these and all three were transform faults of some sort, right? So let's say this is this way, so and let's say this could be anywhere like this. In this case, right, whatever the configuration of the three plates, whatever the velocities of A, B and C, and whatever relative velocity triangle you draw here, right, they would have to be parallel. So any triangle that you draw, let's say like this, so one of the lines is to be parallel this way, the other one would be this way, the other one would be this way. Obviously, you will never get a common point of intersection. So an F triple junction is always unstable. Okay, an FFF triple junction is always unstable. So we know now that it's possible for an FFF triple junction to be always be unstable. So it's a configuration that you will never actually see in nature, right? It's something that will not be seen simply because this configuration is unstable. Let's look at another kind now. This is a different kind, a ridge triple junction. So what about this? So this, let's take a very geometric example, right? For no particular reason, it doesn't really matter. But let's say it's like this, and you have plates A, B, and C here, right? And they're all spreading orthogonally, right, about their own ridges, this way and this way. Now, as you may have guessed, right, when we draw in the relative velocity triangle, so you'll have some relative velocity triangle, and it doesn't really matter, right, what the configuration is. You'll have the perpendicular bisector of this line, the perpendicular bisector. So Let's, whatever way you draw it, the perpendicular bisector of this line, the perpendicular, sorry, this is the perpendicular bisector of this line and the perpendicular bisector of this line. Obviously, they will always meet in one single point. That's a rule of geometry, something that Euclid has told us. So we know that they're going to meet at a point, and that would be the circumcenter. The circumcenter, right? So that circumcenter of the relative velocity triangle will actually represent the relative velocity of the triple junction with respect to each of the three plates. So just imagine that the triple junction was somewhere here. So if a person was on this, situated on this place, this triple junction would move this way, would appear to move this way with a magnitude of velocity proportional to this. If the person is here, this triple junction would appear to move eastwards. If a person was here, this triple junction would appear to move westwards. So this is not the actual depiction of the relationship here. But anyway, what I'm trying to tell you is that this is the sort of configuration that we would expect to see. So therefore, now you can see that this would be a situation that is between R triple junctions, right? These are always stable. So just as an FFF triple junction, a fault triple junction is always unstable, and RRR triple junction is always stable. So we now have the basic tools or the strategy we need to be able to evaluate, right? What would the types of triple junctions be? Now, this is just an extract from the famous paper of Mackenzie and Morgan in 1969 in Nature, in which they talked about triple junction geometries, and what they talked about were the 16 possible types of triple junctions. Once again, of these 16 possible types that we've talked about, of the 16 possible types of triple junctions that are indicated, then the ridge is always stable, right? Whereas the FFF is always unstable, right? And you will find various configurations, right, which actually evolve to one another. So most of the others are stable under certain situations, unstable under other situations. So these actually vary with time. So this would be different. The stability or instability would actually depend upon the actual configuration of the boundary and the actual velocities that are involved here. So of the 16 possible types of triple junctions, one you can always predict will always be stable, another one will always be unstable. Now, let's just look at the major takeaways from what we've learned today. We know now that around triple junctions and RRR triple junctions, these are always stable. FFF triple junctions are always unstable, and all other types of triple junctions are conditionally stable. So there are various conditions under which these triple junctions can be stable. So just to conclude then, the stability of triple junctions, they can be evaluated using relative velocity triangles. There are 16 possible types of triple junctions, of which RRR triple junctions, that is ridge triple junctions, are always stable. Fault triple junctions are always unstable. And all other types, they might be stable under particular conditions. There might be some which actually evolve into other geometries. Unstable triple junctions, by their very nature, they evolve to a different geometry with time. Now, the references we follow here are the same, but I just draw your attention to this classic paper by Mackenzie and Morgan, 1969, from Nature, right, which dealt with triple junctions. And this is one of the last papers, classic papers, which established how plate tectonics and how it works on Earth, and how it effectively controls what happens, the geometry of what happens on the surface of the Earth. So, based that, thank you very much. Enough for today.